Everyone coming in. All right, team, there's me. So, hey, welcome to today's webinar on why the MTBF sucks. So, for those veterans who have been with me in my webinars, yeah, I'm slowly transitioning how I deliver my webinars into more interactive um, experiences like this. And this is the first time I'm doing it, the Shendo webinar in my actual office. And so it's a work in progress. So today's webinar, you do see me at the start and the finish. I just didn't have all the time to be able to go through and make it more weatherman, weatherwoman centric as we go through. But hopefully, if this is this being the last time you'll see me in person until the end of the webinar, it's still going to be a joyful experience for all those involved. But before I start, it's titled this webinar is the MTBF sucks, or actually that's part of the title. I forget what the title is. What the MTBF sucks, and here's why. And it is a pretty ordinary metric, but there are, for example, asset managers out there who will use the MTBF to track progress in terms of how their maintenance is going. And so I know Fred has dedicated an entire website to there being no MTBF whatsoever, and I completely concur with the underlying rationale. But there are scenarios out there where the MTBF can work. The problem is that it often is once it sort of weasels its way into an organization, it seems to like COVID take over the world within that organization and sort of dominate reliability discussion thereafter. In the world of maintenance maintainability, it's actually relatively okay, but we're going to talk about reliability today. And reliability starts with understanding how your product, your thing fails. And so again, for those veterans, here is a repeating theme, which is the ball bearing. Now, the ball bearing is a wonderfully simple device, wonderfully simple creation. Now, I love it. It's fantastic. It is one of the most amazing things there is, and it came into play when we started designing bicycles and things like that in the 1800s. It does an amazing job of supporting a rotating shaft with minimal friction. And of course, one of the thing that the Industrial Revolution started to create was machines that could make shafts rotate, and we could sort of pipe those shafts through factories, through cars, to do amazing things like turn wheels and manufacture railway sleepers and things like that. Now, the problem with ball bearings, just like everything else in the world, is that it will eventually fail. And failure is a random process, which means that seemingly identical ball bearings have the temerity to fail at different times. Now, when we say seemingly identical ball bearings, what does that mean? Well, that means that if we take two ball bearings that are, oh, that little arrow is there, that's very, very amateurish of me, that appear to be identical from our perspective, they have the same serial number, come from the same batch. They might have the same serial number, sorry. They might come from the same batch, from the same supplier. They might be right next to each other on the conveyor belt on which they were assembled. Yet they are fundamentally identical to us because we can't see any difference between the two of them, even though we know, for example, the one on the left might have an impurity right there, and the other one on the right might have a dislocation on the outer race right there. And so we know that even though we can't tell the difference between the two of them, they're manufactured to maybe a fantastic level of quality, they're going to be microscopic differences between the two of them. So they're not exactly the same or identical, but from our perspective, they're indistinguishable. So when it comes to identical, the word identical, when I talk about identical in the world of reliability engineering, something is essentially identical, or two items are essentially identical if the decisions we would ordinarily make based on those seemingly identical components would be identical. That is, you wouldn't look at the one on the left and treat it differently compared to the one on the right. Now, if you can see a scratch or a crack or something like that, then we can start to see a difference, which means we don't treat them identically. So for all intents and purposes, something is identical to something else if from the information we have regarding it, we would treat them identically. So more along the lines of them being indistinguishable, even though we know that they're going to be different if we were to take a microscope and zoom in to the atomic lattice that makes up these different ball bearings. And the random hand of failure, for those, again, those poor old veterans, you're getting sick of this, I know. The random hand of failure here represents all those different random processes and uncertainties, which means that seemingly identical ball bearings will fail at different times. Now, the horizontal axis here, or this horizontal line, I should say, represents time to failure. And in reliability engineering, we know time is analogous with the age or the extent to which something accumulates damage over time. So for ball bearings, time is measured in cycles or revolutions. This is not a failing of nomenclature by any stretch. It's just that there are so many different ways to measure the age of something that for simplicity, we use the term time to failure or TTF to essentially describe how old something is. Now, that doesn't mean that we can just put our brains into neutral. We need to think about how things age. And so the way we measure the age of a ball bearing will be different to the way we measure the age of a car tire, of a small satellite, all the different things we've talked about over the years. And so one large factor that influences how long a ball bearing lasts is particle contamination, which is something that you can fight against when it comes to ball bearings, but eventually particles will get into the inner and outer race and the steel balls that separate the two and essentially cause localized stresses, which accelerate local spalling and fatigue, which cause the thing to fail. Another key factor is misalignment, where when we install the ball bearings, the shaft does not perfectly align with the housing that contains the ball bearing, and we have this, any misalignment will introduce, in many cases, a huge amount of stress to the components or the elements of a ball bearing. Then there's disassembly damage. So those larger ball bearings which get pulled apart to be maintained. Every time you do that, you will incur some damage. Insufficient lubrication, another factor which drives how long it takes for something ball bearing to fail, and eventually this will get to most. Then humidity that causes corrosion, excessive loads, manufacturing defects. In fact, you can see manufacturing defects as one of the smaller factors which drive the time to failure of a ball bearing. So these are the different factors that we know of which drive the time to failure of a ball bearing. And that means that seemingly identical ball bearings whose times to failure are represented by these blue dots will occur at different points in time. But just because something is random doesn't mean it is unpredictable. We can see straight away that data point density is much higher there in that little region we just circled. And that means that our ball bearings are more likely to fail right there. So even though failure is a random process, there are patterns and behaviors that will always emerge. Now, a lot of people say, well, something's random. It means it's equally likely to occur at any point in time. That's not true. For example, the height of a human being is a random variable. It's influenced by genetics and diet and exercise and all sorts of other things. And so the height that each one of us ultimately grow up into is a random variable. But to say that because our height of a human being is a random variable, that we are just as likely to be 10 meters or 30 feet tall as we are to be 1.8 meters or 6 feet tall is just nonsense. We know that random variables have different failure patterns that we can learn from. And in fact, there is no natural phenomena where it is equally likely for a random, especially a continuous random variable, to be equally likely to fall upon some value. The closest we have is the dice, where it's equally likely for you to roll a 1, 2, 3, 4, 5, or 6. But that is very contrived and not how we would describe most random variables. And so it isn't easy to see the density of the pattern we're talking about with these data points right here. Another better way to see these things is by using a histogram, which uses bars, which uses bars to be able to sort of visualize the density we've just been talking about. So when it comes to seeing a pattern, now something is really starting to emerge. You can see that histogram with the bars, which represent the different densities, are now all about. Well, let's get there here. They sort of start to show more visually the approximate likelihood that the ball bearing will fail at a particular point in time on that horizontal axis. And so you can see that this pattern is not very smooth. And one way to smooth this out is to get a lot more information. So how do we get more information? Well, one way of getting more information is to get tons more information, where we will bring back our random hand of failure and have an incredible number of ball bearings tested or measured or otherwise observed until they fail. And now you can see we have a ton of information right there. Our histogram is now a lot smoother. And because it's a lot smoother, the pattern is starting to emerge. Now, that information is not free. It comes at a cost. And you can see the huge number of blue data points we have, each one represents a single ball bearing. In many cases, you simply cannot test that number of ball bearings or anything else. But let's just say we were to test an incredible number of ball bearings or anything else, any other component we're interested in understanding. Eventually, our histogram would collapse to a beautifully smooth curve. This is what our histogram would look like. We had a huge amount of information or data. So let's call this the ultimate histogram. And this captures the random nature of the times of failure of our ball bearing. It doesn't tell us when the next ball bearing will fail, but this has all the information we can possibly get about the times of failure of that ball bearing. And the boring mathy definition of this shape, or at least the line at the top of this shape, is called the probability density curve. Now, before I move on, before I move on, computer, are there any brave souls out there who are wanting to try and define the mean of something? If you are, please feel free to show your definition in the chat window. Anyone want to? What's the mean of a random variable? Anyone typing? I sense one of the reasons I'm not getting a lot of the point. Here we go. The point in the distribution that divides the area underneath in two equal portions. Okay, there's one definition. Well done, Mahendra. I respect your courage. Quang. I apologize for mispronouncing. Where the areas under the curve to the left and the right of the mean are equal. So I think Mahendra and Quang are talking about, it's describing the same criteria for the mean. And I think this highlights one of the problems we come across in the world of engineering, reliability, quality, and statistics. The mean just feels such a well-known value or well-known metric that when it comes time to actually talking about it, not everyone's willing to step forward. Carl writes, the mean of the random variable, you essentially calculated a weighted average of all possible outcomes. Well, the average is one way of a lot of people see the average as synonymous with the mean, where the weights, the probabilities are the probabilities of each outcome. For a discrete random variable, this involves multiplying each outcome by its probability and then summing these products. For a continuous random variable, which time to failures are, this mean is found by integrating the product of the variable and its probability density function. So the probability density function is a thing that describes this curve here. So Carl, you're not wrong, but let's look at these definitions, or come back to them ever so in a very short period of time. So if we look at the probability density curve and go back to the ultimate histogram shape it creates, and if we were to balance this ultimate histogram shape right there on the balance point, well, that's the mean. And so if the random variable in question is the time to failure of a ball bearing, that's the mean time to failure. If the random variable in question is the time between subsequent failures of a repairable system, and that's the mean time between failure. If we are using any sort of random variable, such as the height of a human being, we often use the Greek lowercase letter mu to represent the mean of that random variable at the top there. So you can see, hopefully, or visually, what the mean of a random variable is. If you can create this ultimate histogram shape by hypothetically observing an incredible number of things, random variables, or if you're able to somehow create this ultimate histogram shape through analysis, which you can do, you know, balance that point, balance this shape perfectly, or that balance point, that's the mean. Now, one of the reasons we use the mean is that it's from a family of other statistics or metrics where we attempt to define or describe sort of the central or typical value of a random variable. And so because of that, we often have lots of different ideas about what the central or middle value is. In fact, the mean sort of comes from the French word for middle. And it's not a perfect definition of what a typical value is, but this is what the mean is. It's the balance point of the ultimate histogram shape. So Mahendra Kwang, are we still confident that your definitions where we divide the area under said curve into equal halves, does this visual change your definitions, or are you still sticking with? What you got? Same? Okay. No worries. So Carl's not wrong. It's the integral, the weighted average underneath the curve. But in a way, all the weighted average does is essentially find you the point where, if you were to balance it, that would be the mean. It's a center of gravity, for a lack of a better term, for our ultimate histogram shape. So let's look at this ultimate histogram shape and mean in a little bit more more detail, I should say. So here is a random hand of failure for small satellites. And when I say small satellites, I mean very small satellites. Now this ultimate histogram shape, you can see, is now hugging the vertical axis. And this is not how the human brains like to visualize random things. We like to have ultimate histogram shapes. I apologize for that video bar popping up as often as it is. I wish it wouldn't. But we like ultimate histogram shapes, which sort of have a mountain look, or a hillock, or sort of a peak, where it sort of suggests that it's more a random variable value is more likely to be around some central value and get less likely as we move away. Now you can see here, perhaps incredulously, that I've still got the balance point at exactly the same point for this particular ultimate histogram shape. Describes the times to failure of small satellites. You can see that the mean value is actually relatively unlikely. You can also see that it looks like a large number of data points to the left of the mean. And this is what happens when we have something that fails almost exclusively due to wearing or infant mortality, which is precisely what small satellites do. And that means that a fraction of products carry problems that cause early failures. And so when a product fails, those that still work appear to become more reliable. In a way, this is what screening does but you're just using small satellites in the real world, and they're getting screened as they fail through normal use. Now, small satellites are devilishly difficult to manufacture. They are low volume, they're job produced, they're not mass produced. There might be months between production runs of 2, 3, 4 small satellites at a time. None of the components they use are designed to be used in space because most electronic componentry these days are mass produced for smartphones and computers and the rest, not small satellites. And of course, these poor little things often get damaged during launch and damaged during insertion into low Earth orbit. And so virtually every small satellite, in fact, virtually every spacecraft has been shown to fail in a way that aligns with wearing or infant mortality because they all have these defects that essentially doom many of them to an early death. And the ones that tend to last longer are the ones that sort of by definition are the ones that have fewer or smaller defects. And so they appear to be more reliable. And they're creating this very non-intuitive ultimate histogram shape where statistically the most likely time to failure is 0, believe it or not, because that ultimate histogram shape goes all the way up to infinity. And so examples include manufacturing defects. Examples of failures are those that are caused by manufacturing defects, those failures caused by assembly or installation error. You can see these are two activities which will introduce problems or issues with a portion of the population. Interface issues, software bugs, another classic wearing or infant mortality failure pattern, damage during transit/launch for small satellites. So here, all of the above, you can see there's tons of different ways we can create a failure pattern based on infant mortality or caused by infant mortality or wear-in. But you can see the mean, the balance point hasn't moved at all. So Mahendra and Quang, still comfortable with your definitions of what the mean is? Right, love it. Love the conviction. So let's look at a different shape now. Let's look at the mean time to, look at the same shape, got ahead of myself. Now the mean time to failure is right there. So the reason why I'm torturing Prol, Mahendra and Quang is not because I hate them, but I respect their courage. It turns out that unfortunately for Mahendra and Quang, the area under this ultimate histogram shape to the left of the balance point is 80% of the total area under the probability density curve. So for small satellites, we expect 80% of them to have failed by the mean time to failure. Now, this doesn't make a lot of intuitive sense because the balance point is perfectly balanced, but it's the shape that creates this difference. You can see that this curve is clearly not symmetric. You can see that there is the shape on the left-hand side of the balance point is very different to the shape on the right. Now, the reason why it is perfectly balanced, even with 80% of the total area under the probability density curve to the left, is because the area to the right, the remaining 20%, extends so far out to the right that it balances based on the distance that area is away from the balance point. As you know, or as a lot of people should know, when we talk about moments and levers and things like that, the further away you are from a fulcrum, the more force you're able to exert. So essentially, those 20% of 20% of all data points that extend all the way to the right are able to create a moment which perfectly balances all the other moments from the 80% of data points on the left, because they are very close to the mean time to failure. So unfortunately, Mahendra and Quang, the mean is not the point where you divide the area under the ultimate histogram shape into equal portions. Does anyone know what that point is called, just to see if any statistical geniuses are out there? What's the point? Median, correct. Well done, Kevin. So the median is the point which divides the area under the probability density curve into two equal halves. And so the mean will equal the median if the probability density curve is symmetric, but when it's not symmetric, they are different. And so I'm going to add a little sort of gauge on the right-hand side. You can see we have a sort of gauge or continuum at the very bottom. I'm sorry, Mahendra. I wasn't trying to pick on you, but I do. Hey, tons of respect for you actually throwing your hat into the ring as part of this discussion. It makes these webinars so much more enjoyable. You can see that on the right-hand side, we have this continuum or gauge, where at the bottom of the gauge represents wear in, and at the top, it represents this thing called wear out. We're going to talk about wear out very shortly, wear in versus wear out. Now, I've got this little yellow sort of marker to show that this probability density curve, or this failure pattern, is exclusively wear in. Now, watch very carefully as our ultimate histogram shape and our marker moves away from wear in to what we call wear out. Again, the mean or the balance point will not change as this happens. Now, as we move to exclusively wear out, where we get this symmetric ultimate histogram shape, now the mean and the median are exactly the same, because the data points to the left of the balance of this balancing point are now 50% of all data points. And this is what happens when we, for example, observe the time to failure of something like a tire. And this the tires wear out in a very unique way. Well, not unique way, but very particular way, where the amount of damage that accumulate over time is roughly proportional to how long they've been used, or more correctly, how not how long in terms of time, but how long in terms of distance. And so you would expect a car that's been driven a wheel that's been driven, a tire that's been driven 100 miles to have accumulated about half as much damage or tread loss as another tire which has been driven about 200 miles. And when you have this close correlation between the accumulation of damage and age, you get this wonderful bell-shaped curve here, which is symmetric and describing a random variable in a way which is much more comfortable for us. We love this. We naturally like to see these sorts of curves when describing random things, where the curve shows that the value is more likely around some central region and less likely to move away. This is what our brains tend to think of when we're trying to characterize random stuff or uncertainty. But we only see it in certain components and certain products, such as the tire. So you can see that we are now talking about something which is accumulating damage. This is what it looks like when things accumulate damage. The probability density curve for your system will have a peak if it's accumulating damage in any way. Now, let's remind ourselves what the shape of the probability density curve for our ball bearing looks like. It's different. It's not symmetric, but it also has a peak. And that is another signature of things that are wearing out. So things that accumulate damage are things that are wearing out, which means that every day they're being used, they are less likely to survive the next day, as opposed to the small satellite. For every day a small satellite survives, it is less likely to fail the next day. And wear out can be caused by things like fatigue cracking, where cracks grow over time, oxidation, where things react with oxygen, and corrosion is a very specific type of oxidation. It's based on metals, creep, where solids slowly deform over time under stress, wear, which is what happens for our tire, where it loses tread, lubricant contamination, where contaminants start clouding up your lubrication, diffusion. We're talking about electronic components now, where you have usually metallic or metal atoms slowly meandering their way through silicon crystals. And so we have tons of different ways things can wear out. So let's go back to our ball bearing and look at where, for example, we might want to do something about these failures. What do I mean by that? When things that wear out, things that accumulate damage, are prime candidates for preventive maintenance or servicing. Thank you, I think Chrysostomo. I'm not sure what the registration is shared timely means, but thank you for your feedback. And don't forget, this is recorded. So if you want to check it out in the future, please feel free to come back. So where were we? Yes, things that wear out are great candidates for servicing or preventive maintenance. That is, we tend to replace tires before they completely lose their tread. And we actually know how quickly tires tend to degrade. And we also have things like tread indicators that allow us to replace tires when they're starting to get worn out. We don't wait till they fail before we replace them. And that is something you can only do when things accumulate damage / wear out. So when it comes to ball bearings, let's just say we are interested in finding thinking about when we should replace ball bearings before they fail because they wear out. One way of looking at it is to, for example, pick a number, in this case 10%. Here is with a point where we expect 10% of our ball bearings to fail, that point right there. And that's because the area to the left accounts for 10% of the total area under the probability density curve. And so you can see if we replace our ball bearings there on a fixed interval or fixed duration strategy, we will, at that point in time, expect no more than 10% of our ball bearings to have failed, but we can replace 90% of them, the vast majority, in order to then replace them with brand new ball bearings, which don't accumulate damage, to minimize the chance of the ball bearing failing in your plant. Well, when I say minimize, at least I mean minimize to 10%. Now, another way of looking at this point in time is by referring it to what we call the B10 or L10 life. Now, the B10 life is the time by which we expect 10% of ball bearings to fail. The ball bearing industry came up with this statistic and everybody else loved it. And so what did they do? They said, well, we can't use the letter B for our satellite or tire or chassis or gear stick or whatever it is. And so you'll often see the letter L used to describe these sorts of statistics. So the L10 life is exactly the same as the B10 life. It's just that the letter B is reserved for bearings in general. This is the point by which our ball bearing reliability has dropped to 90%. And that means that 90% of the area under our probability density curve is to the right of this particular statistic or metric. So hopefully you're staying with me so far. Now, we haven't really talked about reliability too much. We talked about the probability density curve. We talked about how there's a failure pattern. We looked at the balance point. We looked at different shapes for different components and different products. But one way of looking at the reliability is to go back to all those data points that we had to create this ultimate histogram shape. And instead of just dropping them on the horizontal axis, we actually plot them in a way where each data point is plotted the height of each data point is based on the percentage of things that haven't failed. And you can see at the very top where nothing has failed, reliability is 100%. On the right-hand side, where virtually everything has failed, reliability is close to zero. Now, this is the reliability curve that corresponds with the probability density curve for our ball bearing. Now, every product, system, or service has a reliability curve, even if we can't see it. It's there. Sometimes we'll do tests to try and guess where this curve is or estimate where this curve is, but everything has a curve. And unfortunately, this curve can change when you change the temperature or the operating profiles or all those other things that make things last longer or shorter. But let's just say that this is the reliability curve for our ball bearing used in pristine conditions. Doesn't mean it will never fail, but it means it fails in a way that we perhaps have some idea about. You can see on the horizontal axis, I haven't forgotten that B10 life, which corresponds with a reliability of 90%. So hopefully you're starting to see that the reliability curve encodes the same information as our probability density curve. The reliability curve is often the curve we're more interested in when it comes to the numbers that help us make decisions. Now, if not everything is working at the start, then the reliability curve doesn't start at 100%. So the reliability curve in this case might as low as start at as low as 85% if we have a 15% of dead on arrival failures occurring. So what does that mean? It means that when we open the box for our thing, our small satellite, our ball bearing, only 85% of them are working out of the box. And these dead on arrival failures do happen. They're often devastating to your brand or your maintenance regime or whatever it is you're working on. But they do happen, and sometimes we need to take that into consideration. A planning figure of 15%, for example, is applied for small satellites because they have to go through a lot to get into orbit. Small satellites are often launched around other payloads. So you might have a spacecraft with a big satellite or big spacecraft in its payload bay or whatever it is called for that rocket or spacecraft. And you just have tons of these small satellites crammed in and around it to essentially fall into the low Earth orbit. And as you can imagine, that involves some rough and tumble. And so they expect no more than 85% of small satellites to start working from when they're first inserted into the low Earth orbit. But notwithstanding, most reliability curves start at 100%. You'd expect that for ball bearings. It's unusual for ball bearings, as rugged and robust as they are, to not work at all when you install them. And so this reliability curve for this ball bearing, or these ball bearings, I should say, starts at 100%. And you can see, for example, we can work out where we expect 50% of our ball bearings to have failed. Now, for Mahendra and Quang, that is the median, the time where we expect half of our things to have failed. So right there is the median, or the B50 life. And so you can see the number doesn't have to always be 10. In this case, the B50 life represents the point in time or number of cycles where we expect half of our ball bearings to have failed. It means we have a 50% failure probability or 50% reliability at the B50 life. And as we move from left to right, reliability will eventually approach zero because everything eventually fails. Now, as a rule, we usually don't care about the trivial thousands or the last 90% of failures, especially when it comes to servicing or overhaul or mission reliability or things like that. We want to get ahead of the curve when it comes, so to speak. Actually, I've never thought of it that way. We literally want to get ahead of the curve when it comes to wear out failure mechanisms and replace things before the probability of failure is unacceptably high. So that's why we see these reliability goals of 90+%. Our system stops being useful after a small fraction have failed. When a warranty in particular, some industries can only tolerate no more than 2% of their things failing during the warranty period before they start losing profit. So we're usually only interested in the first bit of the reliability curve when the small fraction of things have failed. But like I said back a little bit, that the reliability curve and the probability density curve encode the same information. So what does that mean? It means that if I was to put essentially the reliability curve on top of the probability density curve, or the other way around, I should say, we actually are looking at exactly the same random process. It's just visualized in a different way. So the reliability curve can be seen as a right side area under the probability density curve. Now, what in God's name does that mean? Well, let's look at an example. So just follow the animation closely as we trace out our reliability curve moving from left to right until we have 60% reliability. The curve has gone down to the point where it reaches 60%. Now, you might have noticed the area under the probability density curve at the top. It's also changed. It's also no longer completely shaded in. In fact, if you look at that right-hand area, the total fraction of area under the probability density curve to the right of that point, indicated there on each axis, is the same as the height of the reliability curve. And so as we trace out this area moving from left to right to create a reliability curve, you can see that essentially the probability density curve defines a reliability curve precisely. And we can go the other way, vice versa. So every time you have a probability density curve, you have a reliability curve. And so what does that mean? Well, let's get the definition of reliability out of the way. Reliability is the probability that an item will not fail for a designated period under specified conditions. 4 key parts. The definition of failure: will not fail. First thing, you need to describe what it means for your thing to fail. Specified conditions. You can't just assume that something will work in pristine conditions just as well as it would work in harsh environmental conditions or where stress has been increased. We know that we have to treat our products well. Designated period. All that means is reliability changes over time. You can't just use a single number to characterize reliability. Hold that thought. And last but not least, reliability is a probability. And that just reflects the fact that failure is a random process. It's a random process in any scenario where there is uncertainty in the outcome. We hate uncertainty. We love arithmetic. We love 1 + 1 equaling 2. We don't like it when 1 + 1 is about 2, or with a plus or minus some margin of error. We love certainty, hate uncertainty. Whenever we are dealing with uncertainty, we have to deal with probabilities. So remember, I said reliability cannot be characterized by a single number or statistic. And unfortunately, mean time to failure is a single number. Hopefully you've seen how the mean time to failure can be the point by which we expect anywhere between 50 and 80% of our products to have failed. 80% of our small satellites that we're in will fail by the mean time to failure. 50% of our tires will fail by their mean time to failure because the probability density curve is symmetric. Now, Rochelle asks, how about the confidence level? Is this a critical part of the definition as well? No, the mean time to failure in a way is not uncertain, so to speak. Every ball bearing has an actual mean time to failure. It has a balance point of those hypothetical data points of times to failure. What we need to use confidence levels for is our estimate of the mean time to failure. So if you test 3 ball bearings until failure and use them to try and have a guess at where the mean time to failure for all the thousands of ball bearings that will be produced are, sure, you'll have some estimate, but you won't have a ton of confidence. Confidence is a measure of you, not a measure of your ball bearing. And so the more things you test, the more confidence you have. But still, the mean time to failure is as a parameter or statistic that exists, whether we have uncovered it accurately enough or not. Same for the definition of reliability. The reliability curve exists. It's every single ball bearing has a reliability curve. Again, we might use Weibull analysis to estimate, for example, the reliability of a ball bearing after 2 million cycles. And Weibull analysis might take, for example, 30 ball bearing times to failure. So we have a line of best fit plus confidence bounds, and they will tell you that we estimate, for example, that ball bearing reliability at 2 million cycles will be between 98 and 99%. And we say that with a level of confidence of 95%, lots of percents being thrown around, but still, we're talking about our understanding of what the reliability is versus the fact that the reliability is a certain value at certain times. So hopefully that answers your question, Rochelle. So another problem that people often make when it comes to using the MTTF is that they assume it to be a failure-free period. What? The mean time to failure isn't a failure-free period? Isn't that the sort of period we would expect our product to last, the mean time to failure? A lot of people think that. And unfortunately, there's no such thing as a failure-free period at all. And people say, okay, I didn't mean a failure-free period, but isn't the mean time to failure still a largely failure-free period? And the answer is no, as you've just seen. Bare minimum, half of your things will have failed by the mean time to failure. Up to 80% of your things will have failed by the mean time to failure. Now, most complex systems have a combination of wear in and wear out. And so that means most systems will be have anywhere between 50 to 80% of their things fail by the mean time to failure. And so the mean time to failure is one of the most misunderstood terms when it comes to reliability engineering. Now, hopefully today's conversation has, oh, it's zoomed out, damn you Logitech. Hopefully today's conversation has helped you get a better understanding of what the mean time to failure is. It's the mean time between failure is way more useful when you're talking about maintenance and trying to iteratively improve, for example, downtime in plants and things like that. But when it comes to reliability, well, we use the MTTF to try and characterize reliability. It is deceivingly simple. Not many people truly understand what the MTTF is. The biggest issue I have is that people think it's that failure-free period. So when it comes time to setting servicing intervals for a product, they say, well, what's the mean time to failure of the things that we need to replace during servicing? And they go, okay, these 10 things, we're going to swap out the gasket, we're going to filter, etc., etc., etc. The mean time to failure. Okay, so the filter has a smallest mean time to failure, that's 10,000 hours. So we'll set our servicing at 10,000 hours, and that will guarantee that virtually nothing's going to fail. Far from it. You'd expect minimum half of your oil filters to have fully clogged up by that servicing interval. And who knows what the other things are doing, especially if you have a lot of maintenance-induced failures involved. And so just simply understanding that the mean of anything is the balance point of that ultimate histogram shape beneath the probability density curve, hopefully will give you a lot of information, a lot of ammunition to start making better decisions in the world of reliability. So on that note, before we call it a day, we have about 15 minutes left for questions, queries, doubtful points. Are there any questions, queries, doubtful points? Thank you, Matthew. Much appreciated. Mike writes, the ball bearing goes into a system, so it's just part of the total, or can you assume the ball bearing is a weak link? Is that your reliability, like gears wearing in a system, not using MTTF? So that's where you talk about system reliability modeling, for example. System reliability modeling, where you take multiple components, their reliabilities, and then convert them into system reliability performance. So it's when it comes to systems, it's often challenging to characterize which part of the system you're most interested in. If you're talking about preventive maintenance, then perhaps the only components whose reliabilities you want to combine are those that are going to be subjected to preventive maintenance actions. And all the rest, the chassis and the rest of the system, that's part of a higher level overarching system reliability model. So without understanding the exact scenario, you can't easily assume a ball bearing is going to be not part of the discussion. However, there are plenty of machines designed such that ball bearings are going to outlive the rest of the system by some margin. Many vehicles, that's the case. You don't take your vehicle in to have bearings replaced as a rule. Some do, some don't, but many bearings are designed to outlive the typical service life of a system because they're not easily repairable. And so if that's the case, and you've got some really good information to assume that the ball bearing is not going to be a problem, there's no issue with you essentially assuming that it's not going to be a problem as long as it's based on something. So hopefully that starts answering your question, Mike. Any tips on how to change the MTBF culture in a company to a true reliability culture? Vladimir writes, one of the best ways is, well, two best ways. One, money, when you can demonstrate how much money is being lost by assuming the MTBF. And second thing is, or you almost use the wrong finger, second thing is, and I've had some success with this, where you say, well, everyone else is using the MTBF and they are struggling because of it. If we are the only ones who don't use it, then we're going to have a competitive advantage over all those who do. So they're the two main ones. So you start with quantifying how much assuming the MTBF costs, which often is a big deal. The second thing is make the case that if we're the ones who change and everyone else stays the same, we're going to have a competitive advantage that they will not have. My wider analysis course, for example, I talk about how when you focus on the goal that matters, you can find cheaper solutions because the MTBF is in many cases irrelevant. Mahendra writes, got lost a bit on what the peak of the PDF means in terms of failure mechanisms. Could you please elaborate again? Really simple, Mahendra. Things that wear out. As you can see, there are two. There's a bell curve for the tire and that sort of skewed curve for the ball bearing, but they both had peaks. What a peak means is that there is some tendency of data points to cluster around a central region. Firstly, that's what happens when you have things that wear out. Essentially, things will wear out. The times to fail will tend to cluster around the typical time of damage accumulating to a critical level. And so the fact that you have this peak is just a statistical signature of that event where things cluster if they're used in roughly the same way around the same points of damage accumulation. That's all it means. And so that means when you do your data analysis, and if you were to see that peak on your ultimate histogram shapes, you don't need to do any RCA to confirm that your thing is wearing out. Does that, let me know if that doesn't make sense. Yes, so the cluster is often driven by the dominant failure mechanism. So for ball bearings, it's spalling, which is a type of fatigue particular to ball bearings. And of course, you've got complex systems with multiple components failing in different ways. You might not get that beautifully smooth probability density curve because each failure mechanism has its own. But hopefully that answers the question well enough. Regardless of how smooth that probability density curve is, if there's a peak anywhere, in fact, you might even have at the very start, I'm not sure if I'm being mirrored or not, the very start, you might have a little bit of infant mortality, a little sort of ramp, then it goes down, then it gets this peak. Hopefully that's doing the right to left thing well. And that might mean that a small percentage of your things are failing due to infant mortality. They weren't installed correctly or whatever it was, but the vast majority get through that and wear out at that peak. So hopefully that answers that question. Okay, so let's go back. Rochelle writes, what does this equation mean to you? R equals E to the power minus T over MTBF, if anything. That's the reliability equation that often gets rammed down your throat. And I do other webinars and teach other courses where I explain that that is what happens when you have what's called a constant hazard rate. Now, when I do my constant hazard rate lessons or exponential distribution lessons, I start with a couple of examples. One is a naked mole rat. Those of you might remember the naked mole rat. It's one of the very few animals in the world which is shown to never get old. It doesn't die of cancer, heart disease, or anything else. The only time a naked mole rat, and this thing is ugly, the only way one of those things dies is if it gets injured or eaten. It doesn't get old at all. The other thing I show is a coffee mug. Again, if you look at tombs of Egyptian pharaohs and Roman emperors and everything else, one of the few things that survives all the time is the terracotta pots or the ceramic pots, unless they are hit by something. So essentially, things that are made out of ceramics, the only time they fail is when we drop them. So what does that mean? A naked mole rat is just as likely to die today as it is 100 years from now if it's still living. Same with a coffee mug. Those two things, they don't wear in, they don't wear out. So that equation there, Rochelle, is for a reliability of a system which doesn't wear in and it doesn't wear out. It makes the equation really simple, but it describes virtually nothing in terms of actual failure mechanisms. It helps you pass CRE exams and university course exams as well, but nothing fails with a truly constant hazard rate where you can use that reliability equation. So hopefully that helps. Kevin writes, I think the MTTF can be useful when communicating to non-reliability personnel management, etc., but only if it is part of the description. For example, a comparison of a L10 and a MTTF for two different designs. It can provide an area of the scale parameter of the distribution. What say you? Well, I'd argue that as soon as you start talking about scale parameters, they're going to be lost on your non-reliability personnel. And so I've found that as a rule, we need to really drive home on the metrics or the performance goals that matter. For example, is it downtime per fortnight? Is it the warranty reliability or number of warranty returns, for example? What is it? And or the number of ball bearings failing before we service them. So when you have that vicious focus on performance goals that matter, then that's the only language you tend to need. So I'd say that as soon as you start talking about shape parameters and scale parameters to non-reliability personnel, you risk losing them. That's my main piece of feedback. Matthew writes that reliability equals speed by load by time. Is that true? That's not true. So for example, I can't think of the mathematical basis for that. In that reliability would increase, for example, if speed is increased, or if load is increased, or time is increased. If any one of those three things increases, then reliability increases indefinitely beyond 1/100%. I can't, unless there's some context to that statement by itself, it's not even a little bit true. Thank you, Mahendra. Carl's got a little dissertation on naked mole rats. Vladimir writes, to me, the MTBF is only useful in very early design stages when you can compare two designs and then for PCBAs only. Completely agree with that. The only risk with that, Vladimir, is that I've walked down that path several times myself. But once you have the MTBF in a spreadsheet in the early design period, it just, for some reason, a deity, some sort of Excel-based deity or God comes into play, and that never gets touched. That number survives the entire production process. No one looks into it. Someone said, okay, someone's done reliability stuff. Let me go over here and do what I want to do. So that's the only main risk I see of using the MTBF early, but I do agree with what you were saying. And you agree with what I'm saying too. We are furiously agreeing. Got 5 more minutes. Are there any more questions, or did I not answer any question well enough so far that I need to have another go at? I missed a couple, did I? Sorry, Fred. Do you teach on the use of reliability growth, Mike? Yes, I do. I haven't published that course yet. One of the things, sorry, I haven't publicized that course. Probably I should get onto it. Do you want to learn about reliability growth, Mike? Right. We talk afterwards. Sorry, now I see some questions I missed. Uh, Metapon writes, what is the difference between the MTBF calculated from the probability density function and the way the classic book uses MTBF equals accumulated operating time versus number of failures? Technically, from one perspective, with a bunch of assumptions, that's true. Now, the MTBF from a probability density function, all ball bearings have an MTBF. All computer mice have an MTBF. We just might be able to do some analysis or testing to get a better understanding of what that MTBF is. So if you have ball bearings with an MTBF that exists, we could put those ball bearings into and let's just say the ball bearing is the only thing that fails in this plant. And we only have one ball bearing. So one ball bearing fails, replace it, keep using it until it fails, replace it, keep moving, so on and so forth. If that's the case, that eventually, once you've done enough of those scenarios, and the MTBF will be exactly the same as the MTBF under the probability density curve. However, there are tons of assumptions and tons of limitations on its atom. So the MTBF, let's just say that you use some form of preventive maintenance. That means that you replace the ball bearing at the time you expect that 90% of them will still be working, because that's proactive maintenance. So that means that you only have, between each servicing interval, no more than 10% of your ball bearings failing on average. And so that active servicing will reduce the relative frequency of failures. Now, the MTBF of the ball bearing hasn't changed. It's just that you're doing something about it before that failure affects the system. So if you're doing any sort of preventive maintenance, then the MTBF of that system itself will not align with the MTBF of your ball bearing. And it gets even more marked when you use condition-based maintenance. So if you have some sort of vibration monitor for your ball bearings, which is very, very, very powerful, which means that as soon as you detect spalling starting to happen, you replace that ball bearing, there's a chance that you will eliminate virtually every ball bearing failure, because you are able to detect the vibration, the telltale signs of imminent failure, take it out, put a brand new one in, and in one perspective, have precious few failures. Again, the MTBF of the ball bearing hasn't changed. It's just that, again, you're doing something about it. So the other thing I'll add too is that when it comes to testing, if you have a ton of ball bearings, and so 100 ball bearings, and you test them for 2 million cycles, and 30 of those 100 ball bearings have failed, so 70 are still working, the only time the math works, we divide the total test duration by the total number of failures, so 30, even though 70 are still working, and you get an unbiased estimate, is if those ball bearings have a constant hazard rate, the constant failure rate that I was talking about with Rochelle. And so if you still have things that are still working, the whole total time divided by number of failures creates an inherent bias for things that wear out or wear in. So hopefully that answers your question. The system MTBF is total duration divided by total number of failures, but that can be a long way removed from the component MTBFs if you're proactively doing something about them before they fail. Does that answer your question? Thank you, Medical. Fred, have I missed any more? I'm just scrolling up to see. Rochelle asks, what tool are you using in my presentation? You mean for the aesthetics and everything? Well, for the statistical animations where those data points are falling down, that's based on software I've coded in MATLAB, where we have those data points bouncing and then creating reliability curves and everything else. And the rest of the animations, believe it or not, me and my team are developing in PowerPoint, we use a stylus and a drawing tool to create those very simple aesthetics and animate them in and animate them out. So it makes sure that they're clean, crisp, and do not distract. Does that answer your question, Rochelle? That was not a question I was expecting today.